Thank you all for watching this presentation today. I'm going to present our ongoing work on Roundwood degrade at Forest Research. This is an apparently obvious question. We are investigating a problem, we should surely know what the problem is. So yeah, Roundwood degrade is about the occurrence of cracks in standing trees that lead to log rejection at the sawmill. Great, but cracks are actually not a simple thing, as it's very well shown in this image I borrowed for Napier's blog. We should then rather say that Roundwood degrade is about the occurrence of many types of cracks in standing trees that lead to log rejection at the sawmill. Further, it is still unclear what actually triggers the cracking, with many factors having been reported to cause the problem. So Roundwood degrade is then about the occurrence of many types of cracks in standing trees triggered by a number of factors that lead to log rejection at the sawmill. Conclusion: this is a rather complex issue that requires a multidisciplinary approach. With all this in mind, we believe it is important to set some guidelines to address the challenges posed by Roundwood degrade. In the first place, we need to be able to determine what the impact of cracks is and whether it is actually worth we go any further in our research. Secondly, we need a good description of the problem, of what is actually going on. And this is with the aim of trying to understand the mechanism behind cracking and eventually to provide a solution to the problem. In terms of determining the impact, we will need to know what proportion of trees is damaged every year and which species are affected. In this respect, it is important to work with the industry in the same way Napier has done by deploying their questionnaire on degrade. Thematic events focused on degrade could be useful as well. We also need the problem properly described to know the angle of attack we will need to take more precisely, which kind of crack, where do they occur, are relevant questions. Again, collaboration with other search members will be key. Determining the triggers of cracking is the most academic part, if you like, of our work. In the first place, it is important to establish clear sample protocols to collect the data to be able to carry out any sound analysis. Given the multidisciplinary nature of cracking, it is also key that we work together with other researchers from other areas, for example, other forest research science groups, and obviously with those that are closer to us, which is thus Napier University. We lead to solutions for the sector. For example, we may be able to forecast where and when different types of cracks are more likely to occur, or we may need to identify new lines of breathing, depending on our research shows. Those solutions are still obviously hypothetical. Let me introduce now a case study with the work we have been doing around the mechanisms behind a specific type of cracking in a very specific location. This is part of an article Rachel Davison from FR is preparing. The case study consisted of a Norway spruce plantation located in Thornhill near Dumfries. The trees were about 40 years old and many of them presented a good deal of longitudinal scars, which is obviously a synonym of cracking. The stand was about being harvested, which gave us a unique opportunity to study the issue. Our objectives were in line with what I just explained. We wanted to establish a sampling protocol first for this specific case, then to determine the kind of crack occurring here, and then to identify the triggers. And this was by mapping the crack trees. This could reveal any kind of soil issue, for example, and by finding the relationship with climatic variables. But before going into the details, let me show you some background. Cracking is a two-dimensional problem. As we all know, there must be some environmental trigger that leads to a certain degree of water imbalance within the tree, which in turn leads to internal tensions and eventually to the collapse of a group of cells and then to cracking. But for that to happen, there must also be a vulnerability within the tree. The problem here is that both triggers and vulnerabilities are not entirely understood. The literature suggests that trees may be more vulnerable to cracking when rings with low early wood density exist. These rings will occur in years of fast growth. Alternatively, or additionally, it has also been reported that rings with high late wood early wood ratio will be more prone to collapse under stress. And this is because the stronger late wood may pull and tear the weaker early wood. This kind of vulnerable rings will occur rather in dry years, because the late wood will start to form quite early in the year. On the side of the triggers, processes as different as freeze and then thaw, frost drought, summer drought, or soil issues have been suggested to be behind the water imbalance. We'll focus on these environmental triggers for now. Back to the experiment, we basically had data from 12 trees, from which we were able to determine the year of crack occurrence, and in the near future, ring density may be available as well. In parallel, we had climatic records for the whole rotation period. So, coming back to our objectives, we managed to establish an effective sample protocol. And we identified the type of crack. The image from the neighbor's block turned out to be very handy, as you can see. But while these things are key from an operational and data gathering point of view, it is the mapping and the triggers investigation that led to some interesting findings. As you can see in the image on the left, there were two types of layout in the plantation. The rows of trees were deployed almost north-south above the red line and almost east-west below the red line. And as shown in the figure on the right, only 2% of trees presented scars and then therefore cracks above the red line, but about 25%, 1 in 4 trees were damaged below that line, and I will come back to that later. When it comes to the triggers, we modeled the probability that a crack occurs in a given year, provided that the tree is cracked at all, as a function of the climate condition of that year. We tested a number of variables as surrogates of very cold, very hot, and very dry conditions, all of which seemed possible candidates to trigger the cracking, as I explained before. We also tested a surrogate of the annual oscillation of the water balance, which had been suggested by Jim Colchester out of his own observations to be a possible cause of cracking. And our results suggest that Jim may be quite right actually. Oscillation in the water balance was actually the only significant variable affecting the probability of crack occurrence. The larger the oscillation, the more likely the cracking. So if a year has a very dry period and a very wet period, then cracking is more likely. That's great, but why? Here there is a hypothesis. Remember that the plantation was next to a river. The image on the left represents a scheme with a normal water table level within root ridge, so trees are happy. Now consider that there is a period of waterlogging. This may lead to the death of part of the roots in the deeper part of the soil profile. If shortly followed by a period of water deficit, the roots won't be able to efficiently reach the water resources, which obviously means troubles downstairs and water imbalance and internal tensions upstairs. If on top of that we consider the sense of the stream and the plantation layout, it may well be that the drainage below the red line were worse in time of waterlogging, which would have led to a higher occurrence of cracks in that part of the plantation. Our data are of course quite limited, so we have to look at the evolution of the water balance oscillation over time and the years where cracks occur. Those are the vertical dashed lines. Just in case we see something interesting. Considered locally, it looks as if the cracks actually occurred in years with higher oscillation. However, much more serious water balance differences were took in different years in other years. Why didn't they lead to cracking? One possibility would be that the relatively low water requirements will imply less internal tensions even if other conditions are extreme. In this respect, the seedling stage in the early years and high competition, which was evident in this case from the rings widths from approximately 1988, are physiologically less water demanding stages. This may explain why cracks only form in the central years of the rotation, where water requirement was more important. It's a lot to be understood though. This is our model predictions with the probability of cracking in the y-axis. As you can see, the model suggests that even when the water balance oscillation is very low, about 4 in 10 rings will collapse. This is not so, as we know by experience, and therefore more work is needed to understand what has happened to those constructed years, like for example a very dry period happening there or something like that. We need to study more in more detail this. Looking now into the future, we need to go further in studying the triggers through new case studies with the help of forest owners and managers. We will then be able to carry out new standing stock surveys and to investigate what we see in the light of more detailed climatic and soil data. But we also need to study what makes trees vulnerable. This can be by taking disc or cores from cracked but also non-cracked trees, by measuring early wood density, by determining the ratio between late wood and early wood, by using mechanistic models to understand how the water potential affects the cells physically, as our colleague Henderson is doing in forest research, and by testing whether the vulnerability can be managed through breeding or silviculture choices. In practice, we believe that we will be able to produce a crop probability map through all that work. This will be similar to the 16 wind damage probability maps, of which you are surely aware. This will allow determining whether any action need to be taken at all, the situation of the current timber resource, and perhaps different ways of managing and planting in the future. This doesn't necessarily mean any dramatic changes, don't take me wrong, but something of the sort: make sure your Norwest Place plantation is well drained. As said before, new breeding lines could be envisaged in collaboration with Gustavo and Richard from FR, but only if there were enough evidence that no cracking properties can be inherited. And that's all from us. Before finishing, I would like to acknowledge Jim Colchester from Buccleuch Estate and James Johnson's Whole Mills for their ideas, help and availability with this piece of work. Thank you all for listening. Happy to take any question or to listen any suggestions you may have. Thank you very much.